We have seen that a beam of light can be viewed as a wave or a stream of tiny quanta that we call photons. We've learned that each photon carries energy directly proportional to its frequency. Early evidence for the particle-like nature of light came from experiments done in the latter part of the 19th century when several investigators noted that light could eject electrons from various metal surfaces. This ejection of electrons by light has led to electric eyes for opening doors and to a wide variety of other photocell detector applications. This phenomenon, the ejection of electrons from metals by light, is called the photoelectric effect. First, a bit of history. Albert Einstein was the first to convincingly explain the photoelectric effect in 1905, the same year he advanced the special theory of relativity. Experimental verification of Einstein's explanation was demonstrated 11 years later by American physicist Robert Millikan. Interestingly, Millikan spent some 10 years trying to disprove Einstein's theory of the photon, only to become convinced of it as a result of his own experiments. Millikan won the 1923 Nobel Prize in Physics 1 year after Einstein was awarded the same. Einstein received his Nobel Prize for his work on the photoelectric effect, and not for relativity as some people presume. This postage stamp celebrates Einstein's achievement. Note the electrons ejected by the incident light, which interestingly wasn't particularly surprising to early investigators. Electron ejection could be accounted for by classical physics, wherein incident light waves build an electron's vibration to greater and greater amplitudes until it finally breaks loose from the metal surface, just as water molecules break loose from the surface of gradually heated water. But no build-up time was observed, none. It took practically no time for a weak source of light to give some electrons in the metal enough energy to be ejected from the surface. And the striking evidence was that the energy of ejected electrons depended not on the intensity of light, but on the frequency of light. According to Einstein, each photon gives its full energy, E equals hf, to one and only one electron. The electron spends some of this energy overcoming an electric barrier at the metal surface, and what's left over is its kinetic energy of motion once it is free of the surface. So if the frequency is too low, as for red light, the photon won't provide enough energy for the electron to get over the barrier, and it won't escape. Here's a simple arrangement for observing the photoelectric effect. Light shining on the negatively charged photosensitive metal surface liberates electrons. The liberated electrons are attracted to the positive plate and produce a measurable current. If we reverse the polarity of this plate so that emitted electrons are repelled rather than attracted, the current can be stopped. We can then calculate the energies of the ejected electrons from the easily measured differences in voltage between the plates. Yum physics! So light ejects electrons, and a brighter beam of light ejects more electrons, but not more energetic electrons. The higher the frequency of illuminating light, the more kinetic energy the ejected electrons have. A beam of red light, however bright, won't eject electrons because of the barrier effect. But ultraviolet, even dim ultraviolet, ejects electrons. The kinetic energies of ejected electrons is greatest when illumination is with ultraviolet light. Again, E equals hf in action. The only convincing conclusion to be drawn from the photoelectric effect is that light has particle properties. We cannot conceive of the photoelectric effect on the basis of waves. On the other hand, we have seen that the phenomenon of interference demonstrates convincingly that light has wave properties. We cannot conceive of interference in terms of particles. In classical physics, this is contradictory. From the point of view of quantum physics, light has properties resembling both. It is just like a wave or just like a particle, depending on the particular experiment. When it is emitted or absorbed, light behaves more like a particle. When it travels from one place to another, it behaves more like a wave. So we think of light as both a wave and a particle. How about wavicle? Quantum physics calls for a new way of thinking. On some surfaces, light, instead of ejecting electrons, stimulates an electric current in the material. This is the basis of the photovoltaic electric cells that are more and more becoming a major power source. Although the surface being radiated is a semiconductor, not a metal, the principle is the same. This striking photograph of photocells on the roof of the San Francisco Exploratorium was taken by Amy Snyder. A yum photo indeed. Some thoughts about photovoltaic cells. The Industrial Revolution was fueled by the combustion of coal, then later by the combustion of oil and gas. The biggest downside is the pollution produced. Also, these fossil fuels won't last forever. Watch for the next revolution to be fueled by the combination of hydrogen and oxygen in fuel cells, with zero pollution. Hydrogen can be obtained by electrolysis powered by solar cells. How nice that solar power to produce hydrogen fuel is inexhaustible. Fuel cells, now common in spacecraft, are being pioneered in automobiles and buses. Next should be railroad trains, as China has already done, which will relegate overhead wires and third rails to history. The solar fuel cell train is really an electric train, but the electricity is generated on board without pollution. Not provided by outside generating stations or by on-board diesel engines, both of which pollute the air. In tomorrow's train travel, say goodbye to pollution and the infrastructure of overhead wires. So extensions of the photoelectric effect offer great possibilities. I want to leave you with a question. Why will ultraviolet light eject electrons with greater kinetic energies than visible light? And what equation guides your thinking? Until next time, good energy.